5 should be a minute, right? If you finish earlier, that's great.
Okay.
Right?
Yeah, I doubt it, but feel free to stand up and.
Okay, good afternoon, everyone. It's a great pleasure to welcome you to the CFA Colloquium today. It's a great pleasure for me to introduce today's CFA Colloquium speaker, Professor Steve Finkelstein. So Steve, did his PhD back in 2008 at Arizona State University. Then moved on as a postdoc to Texas A&M University before he received the Hubble Fellowship, which he took then to UT Austin, where he actually still is and joined the faculty within a year after receiving the Hubble Fellowship. So I got to know Steve actually as a very supportive person for the junior people in our field. Some junior people don't have it always that easy, I think. And I think Steve is really taking care and seeing that everybody has kind of a good time doing astronomy. Now, this is sometimes hard to reflect in a CV, I think, but when you look at his CV, you see that he's really listed many of the teaching awards that he received, and maybe this is one of the reflections. You see that he really takes care of the younger folks in the field. Of course, Steve has done a lot of major contributions to the high-redshift universe. If I have to describe it in one sentence, he's really discovering the high-redshift galaxies, the highest galaxies we can know about in today's universe. And he really wants to understand how these first galaxies basically reionize the universe. Besides being this world expert of this, he is also involved in many observational programs. As we have heard today at the ITC luncheon, he's very heavily involved in the HETEX survey. Maybe he describes this quickly today, but he was really discussing this a lot during the lunch. But he's also been leading many Keck and Hubble Space Telescope observational programs. And very recently he has received an ERS program from the James Webb Space Telescope. So with his team will actually be the first one to really get the first the JWST images to observe these first galaxies at these early cosmic times. So I think we are very fortunate today to have Steve here to talk about implications of reionizing the universe with low galaxy escape fractions. So Steve, please take it away.
Thank you, Sandro, for the very wonderful introduction. Actually, one slight correction. I actually received JWST time before I ever got a Hubble proposal accepted.
Right.
But I did just have my first Hubble proposal accepted, a 2-orbit proposal. Data are coming in next week. I'll actually show you the source at the end. Yeah, it's a great pleasure to be here to speak in front of you all. So I'm going to tell you a bit of a story about reionization, motivated by trying to reconcile some of the observations over the past decade that have failed to find leaking ionizing radiation from galaxies. And there are some really exciting results, including some I heard about today, that are maybe fixing that. But I'm going to look at least one view of how you could accomplish reionization with low galaxy escape fractions. But before we get to reionization, I want to step back even earlier in time. So if I was going to think of one question that I am most interested in, it would be, when is the onset of light in the universe? When do the first stars form? When do the first galaxies form? This is a beautiful movie from John Wise's group. There are many beautiful movies like this from many groups out there showing you the onset of light. So the Big Bang happened about 13.8 billion years ago. We know that it should have taken some amount of time for a gas to first form and then cool and collapse and condense to form these first objects. Exactly how much time it took, we don't know. But when we look at state-of-the-art simulations like this one, it seems like it maybe could take about 200 million years. So at that time, you're forming the first stars. We have not observed them. We may never observe them, although maybe we'll see them when they explode, if we're a bit lucky. What are these like? We don't know because we haven't seen them, but theory predicts they should be pretty massive. Theory used to predict that you might only form one 500 or 1,000 solar mass star per mini halo. Now we think maybe you're forming a small cluster of stars. But the IMF is probably tipped towards the heavy end, so maybe the characteristic mass is 10 or 20 solar masses instead of 1 like today. Most of these stars will explode, as is being shown in this movie right now, and they'll seed the universe around them with metals. Now, once you have metals, you can have more efficient star formation, what we call population 2 or metal poor star formation. And that is really when you're going to form the first larger clusters of stars, maybe 1,000 or 10,000 stars that I would maybe start to call a galaxy, something forming in an atomic cooling halo and not a mini halo. And so when does that happen? So we have a number of questions. When do these first stars form? What are they like? How long does it take until the first galaxies actually start to form? What are they like? and then what becomes of them to the things that we can actually see. So the things that we can see today with Hubble are orders of magnitude more massive than any of that. And even with Webb, we're not going to get down to the scale of these first galaxies, although we'll get pretty darn close. And so to answer some of these questions, now we have to turn to theory, or really to predict the answers to these questions. And this is our own attempt. This is a study led by Jason Jakes, who is a graduate student at UT. He graduated last year, and he did a project co-advised by myself and Volker Brahm, where we were trying to actually resolve these forming stars in the early universe. And one of the cool things he did was he looked at the transition from pop3 to pop2. So this is showing the star formation rate density on the y-axis versus redshift on the x-axis, going out to these very, very high values. And the blue line is the star formation rate density from pop3 stars. And so he predicts the answer to one of my burning questions. When does it start? Redshift 25.8. Okay, that's a number we can attribute a few 100 million years after the Big Bang. When does pop2 star formation start? Essentially right after. Because once you see the universe with metals, you're going to have more efficient pop2 star formation efficiently. And you can see that pop2 actually eclipses pop3 fairly quickly. One of the interesting things from his thesis is that pop3 didn't actually die. We thought pop3 might be self-terminating and that it's going to spread the metals far and wide and you won't find any pristine mini halos. And we didn't see that, at least not down to redshift 7 or so. It was certainly subservient to pop2, but it still existed. So of course this is just a prediction. It's telling us what might happen. But we would like to observe it, and that's difficult. But one thing that these objects do, the first stars, the first galaxies, and really any massive object, is they have an effect on the universe around them. So anytime you form stars, you're going to form massive stars. Those massive stars are hot. Hot stars make ionizing photons. Those ionizing photons do one thing and they do it well. They ionize. And at those early times, the gas between galaxies, which we call the intergalactic medium, was neutral, and it had been neutral since redshift 1000, and something has ionized it. Because we know today, if we look at the space between galaxies, the IgM is ionized. If we look at redshifts 1, 2, and 3, it's still ionized. All the way back to redshift 5.5 or 6 or so, we know the IgM is ionized. At higher redshifts than that, we'll talk about in a little bit, we think it's starting to get neutral. And so we know something had to come along and ionize this. And we think that maybe it's stars or galaxies, and we'll get to that, but certainly the first luminous sources in the universe had some contribution. And so if we can pin down the very precise timeline of reionization, we can actually start to place some constraints on the abundance, the total luminosity coming from those first stars and galaxies, even if we never actually see them. And so I think there are a lot of reasons to get excited about reionization, and that is the way I get excited about it, trying to place constraints on these very first luminous galaxies out there in the universe. So some of the key questions we have are, when did reionization happen, and how did reionization happen? So let's talk about the how. What was the source of this energy? So I'll give you two ideas. You can make up some other ones, and that's fine. I think there are some interesting ideas, but broadly speaking, we think it's got to be either quasars or galaxies. So let's talk about quasars, or accreting supermassive black holes. So if you look at the emissivity from quasars as a function of redshift, you can see as you go from redshift 0 to higher redshift, it rises, which is good for reionization, but then it peaks at redshift 2 and essentially falls off a cliff, such that by the time you get to redshift 6, and all the action is earlier than redshift 6, it's fairly low, much lower than today. And so that doesn't look very good for quasars contributing. We need to keep in mind, because I'll come back to this later, quasars does not mean all AGNs. We're talking about very, very bright things. So for very bright accreting supermassive black holes, maybe not. When we look at star-forming galaxies, my favorite image here, the Hubble Ultra Deep Field, we found lots of star-forming galaxies in there. And we look at the evolution of, this is showing the cosmic star formation rate density versus time. This is more or less proportional to the ionizing emissivity. You can see that it sort of mirrors what we get from quasars from redshift 0 out to redshift 2. It rises at peaks, and then it falls off again. But the fall off is much more shallow. Okay, and so if you look at the observable galaxies, that's the thin blue line. If you look at an estimate of the total star formation rate density, including things we can't see, it's the thicker blue line. Either way, it's much more shallow than the fall off in the quasar emissivity. And so this gives us a pretty good idea that it's probably star-forming galaxies. At the very least, they're dominating. We don't have a lot of hard evidence that it's that quasars play a big role. So let's assume it's galaxies. This is a game that many of us like to play. And let's see if there are enough galaxies to reionize the IgM, right? We found galaxies at these redshifts, and so it ought to be pretty easy to add them all up and see if you're making enough ionizing photons. So to do that, we need to understand three things. And the first thing is what I call rho UV, or the non-ionizing UV luminosity density. And so this is measured typically at 1500 angstroms. This is the light that we're seeing from these distant galaxies in the Hubble image. So to measure that, what we typically do is we do a search for galaxies, We make a luminosity function that's essentially a histogram of galaxy luminosities. In practice, it's a little bit more complicated. You count them up, you divide by the volume. Calculating the volume is a whole other talk. It's somewhat complicated, but we think we can do this fairly well. And at redshifts of 4, 5, 6, and even 7, various studies agree fairly well. So we make that luminosity function, and then we integrate it to some limiting magnitude, and that's the key, and that gives us this quantity. And so we need to integrate it to some limiting magnitude because the faint end slope approaches -2 or even gets steeper than -2, and then you can't integrate it analytically. It diverges. So you have to pick some stopping point for your integral. And that actually makes sense because massive stars don't form all the way down to luminosity of 0. There's some minimum unit of mass. The absolute magnitude of an O star is something like -5 or -6, so that's a reasonable stopping point. That might be too far because we don't think that galaxies should actually form efficiently all the way down to a single star. And so we'll talk a little bit more about this in a little while, but a common assumption is a limiting magnitude of -13. This corresponds to a halo mass of something like 10 to the 9 at redshift 7. And so if we take our luminosity function and we compare the integral of that, or the total luminosity density, as a function of your faint end limit, if you stop at -22, there are very few galaxies brighter than that, so you get 0. And we're comparing it to if you integrate all the way down to -12. And so if we stop at the UDF limit, which at redshift 7 is about -17, -17.5 or so, you're only getting about a third, or a little bit less than a third, of the total light of galaxies if it goes all the way to -12. If you can go to -15 and a bit, which is maybe where we'll get with the Webb, you're doubling that, so you're maybe getting half to 2/3. But all of it, you need to go 3 times. If you went down to starting at -13, you're getting 3 times the amount of light as you get down to the UDF limit. And so a couple things to take away from here. Number one, if you only look at the galaxies we see, you're doomed to fail. Maybe not that obvious. Why should the universe stop making galaxies simply because Hubble can't see them? That's not that crazy. When you look at simulations, we know we're there. They're there, and now gravitational lensing has shown us, in fact, that they are there. So I would claim that we actually understand this pretty well, and it's really due to a combination of simulations and studies like the Hubble Frontier Field's gravitational lensing, which has found galaxies approaching this magnitude, and there's no hints that the luminosity function turns over at brighter magnitudes. All right, so that gives us the 1500 angstrom luminosity density, so the unit per unit volume. Now we need to know, how do we actually get ionizing photons? We want to convert that to an ionizing photon density or ionizing emissivity, and there is a quantity we can use to do this called C-ion, or the Lyman continuum photon production efficiency. It essentially tells you how many ionizing photons do you get per non-ionizing UV photon, and this is a number which we can use, and we do use. It's a number that you would get if you looked at some stellar populations for modestly metal-poor stars. Seemed reasonable at the time, and I'll tell you why in a second. But if you assume this number and you multiply it by the integral of the first number, then you get the number of ionizing photons. That's how many are actually being made in the galaxy, but they actually have to get out of the galaxy. And this is where the escape fraction comes in, and where I wrote that sentence on a slide for the first time like 6 years ago, where we have the least knowledge. I think it's still true. There have been a lot of gains in really all 3 of these. But it's fairly uncertain. And studies typically used a value of like 10% to 50% for the escape fraction. And the reason why studies like to use these values, number one, is because they were allowed observationally. Nothing ruled them out. And number two is if you take them and you use them appropriately and you calculate the ionizing emissivity by multiplying the non-ionizing luminosity density by C-ion by the escape fraction, it actually works. So what we find is that if the escape fraction of something like 10 to 20%, you integrate the luminosity function down to -13, and without the slope changing, and C-ion is something like 25.2, you get enough ionizing photons at redshift 6 to reionize the IgM. And all is well and good, and we can be done with the talk. Unfortunately for all of us, all galaxies likely do not have uniformly high ionizing photon escape fractions. So these are just a few examples showing you what happens if you take a bunch of galaxies, they're actually stacks, and you look at their non-ionizing UV on the left. This is at redshift 1, this is at redshift 3, and then you look at their filter that includes the ionizing regime for these galaxies. So below 912 angstroms, you see nothing. And I don't remember the value from this one. The upper limit from this study was something like less than a couple percent. And so these studies would conclude that the typical galaxy has an escape fraction of less than a few percent. It doesn't mean we never see ionizing photons. Here are a couple stunning examples of escape fractions as high as 50%. one from imaging, so this is actually an image of the Lyman continuum from this source, and one of spectroscopy. It's a little bit hard to see here, but there is significant photons being detected here between 880 and 910 angstroms from some of Alice Shapley's work. I don't think this means that all galaxies are like this, certainly. What I think it could mean is that most galaxies have fairly low escape fractions, and a small fraction of galaxies have high escape fractions. That's one answer. Another possible answer is that all of these galaxies are fairly bright. Okay? Any galaxy we have seen in any study at high redshift is bright compared to the whole of the galaxy population that's out there. So it could also mean that the escape fraction is a function of some combination of halo mass and luminosity, right? So we're only looking at the bright things. Maybe they just don't have high escape fractions. And so that's something we're going to look at for the rest of this talk, but I will also let you know that because this is a very ongoing and exciting field, there's a lot of work being done, and there are some detections of average escape fractions in like the 5 to 8% level from bright galaxies at redshift 3. And so that's actually very exciting. You actually then run into an overproduction problem. If all galaxies at redshift 3 have an escape fraction of like 8%, you're actually going to exceed the ionizing emissivity once you fold in quasars and things like that. So it's a very fluid field. But we'll go with this problem for the rest of the talk. And the question I had is, can we come up with a model for reionization with lower galaxy escape fractions? We know if we assume 20%, it works, no problem. What if we have to assume 2% or 5%? Can we actually make it work? And so the way we did this was we used simulation-based escape fractions, because if you look at the simulations, most of them predict exactly what I said, that massive galaxies will have low escape fractions, low mass galaxies will have high escape fractions. And so the specific prescription we used was from the first billion years, or Phoebe simulations, but similar results come from a number of other simulations, including Fire and Renaissance. But this particular plot here shows you the probability distribution function of escape fraction for different halo masses. So if we take halos that are tiny, mini halos here, which actually never form stars in anything I'm about to tell you, but if they did, they would have very high escape fractions. Okay, they probably have very low gas column densities. It's very easy for you to blow holes in them when you have a starbursting event. If you look at more massive halos, Phoebe was a relatively small box, so this is sort of as high as they went. That's the red and gray line. They sit most of the time at very, very low escape fractions, right? This is log here. But they have a little blip at high escape fractions when they undergo a starburst, clear a channel, and for some period of time, photons escape. So it's possible that this little blip here is the origin of the sort of oddball Lyman continuum escaping galaxies we see. It's also possible this model is completely wrong, okay? So, but we're going to see what happens. Can we actually make it work with this model? So what we did is we used abundance matching to estimate halo masses along the rest-stream UV luminosity function. So every little luminosity bin on the luminosity function gets its own custom halo mass, and then we randomly sample these distributions and grab an escape fraction for that halo mass, and then redo the exercise from the previous slide where we integrate it up. And you might not be surprised to find out that that absolutely 100% fails. And the reason why that fails is most of the galaxies are in sort of this regime here. And I took a model where I needed an escape fraction of 20%, and now I'm moving it down here to like 1%, or a few fraction of a percent, right? So of course that's going to fail. So we need to do something else. And the something else we did was say, okay, let's not just look at the escape fraction. Let's look at every single assumption we've ever made when trying to model reionization and see how much wiggle room we have in those assumptions to try and make things work with fairly low escape fractions. And so what we've done is we've replaced fixed assumed values for physically motivated free parameters, which we constrain through an MCMC analysis, and we use only model-independent observational constraints. So there are a lot of constraints out there in reionization. They're all good in a sense that they represent an immense amount of great and difficult work, but they're not all created equal in terms of how model-independent they are or how free of systematics they are. So we're going to try and stick to the few mostly model-independent ones. And so we have 7 free parameters, and I'll walk you through them really quickly. And so this is showing you what we're replacing. So we used to assume an escape fraction of 20% for all galaxies, and we're replacing that with these Phoebe simulations, but we're actually scaling those escape fractions up, okay? And the reason why we're doing that is Phoebe was fantastic in that they didn't just use their big box to do the radiative transfer. They did zoom-ins on 70,000 halos, but even those zoom-ins had a resolution limit of about a parsec. And they had, some of the people involved in the simulation had a separate paper where they looked at that final parsec, and it really could still underpredict the escape fraction. And so we allow a simple scale factor where every time we sample those escape fraction PDFs, everything just gets multiplied by one number at all redshifts. So we're not making this redshift dependent. And I'm putting in parentheses here our preferred value, so sort of from the posterior. So something like 5. So we need to take the escape fractions from Phoebe and multiply them all up by 5. Okay? So we used to assume a limiting magnitude of -13 at all redshifts, and we're going to replace that with actually a couple things. The first one is before reionization starts, we assume that you're going to form stars down to the atomic cooling limit, which is a redshift-dependent term. Okay, and so the limiting magnitude will actually evolve with redshift because the atomic cooling limit evolves and the halo mass function evolves, so abundance matching evolves. But then after you start to reionize a patch of your universe, you're then subject to photosuppression, where gas accretion onto halos is actually suppressed. Okay, and so our model prefers a photosuppression limit of something like 10 to the 9. I'll have a figure to illustrate this in a minute. But we're replacing some quasi-random UV absolute magnitude, which seem to align with simulations, with real physical limits here. We're going to take this constant C-ion value of 25.2 for all galaxies at all redshifts, and we're going to allow it to evolve both with redshift and with magnitude. So galaxies are allowed to become more efficient producers of ionizing photons at higher redshifts and fainter luminosities. We'll talk about why in a minute. And finally, perhaps the most offensive one, is we're going to strike this where we assume that galaxies are the only ionizing source, and we're actually going to allow active galactic nuclei to play a role. We're not going to force them to play a role. We're going to allow them to play a role. And so this is a figure showing the ionizing emissivity from AGNs as a function of redshift. This green curve comes from a paper by Hopkins et al. In 2007, which matches a bunch of some older data. And this is sort of the minimum AGN contribution. And the maximum AGN contribution comes from this paper by Piero Medal in 2015 called something like Reionization Can Quasars Do It All, which I don't think anybody, including Piero, thinks is correct, but it does match some observations that aren't maybe quite right, but it's still intriguing. So essentially what we do is we let the AGN inhabit anywhere in this space. So we're not forcing them to contribute, they're simply allowed to. They could lie along this line and not contribute at all. Okay, and I'll show you what happens later when we force that. So those are our free parameters. What did we actually use as constraints? So from quasars are great because they're a direct probe of the neutral gas at nearby redshifts. There are a lot of quasar measurements out there in the literature, and many of them are systematically limited by assumptions of the shape of the quasar spectrum. And so we use this mostly model-independent analysis from Regrier et al. In 2015, where they actually stacked a bunch of quasar spectra and looked at the fraction of pixels in the Lyman-alpha and Lyman-beta forests that were actually dark. So they don't have to model the intrinsic shape of the quasar. They just look, where is there no transmission or where is there transmission? And so their constraints aren't as strong as the independent quasar constraints, but they're still pretty good. Their constraints are these upper limits here. And so at redshift 5.6 and 5.9, they constrain reionization to be 95% complete or more. So there are upper limits there. At redshift 6.1, it's sort of less complete reionization. This is neutral fraction, so the neutral fraction has to be less than 0.4%, less than 40%, less than 5% here. And then, of course, we use constraints from the CMB, so from the optical depth to electron scattering. And this is just a fun historical plot showing you how it dropped from 2003 when I started grad school and wasn't at all interested in this. I'm sure that was very exciting. We thought that was true. Convinced people to build a $10 billion space telescope, so I think that was good. But it sort of dropped, so we don't have to justify JWST as much these days, but that's okay. So tau is pretty low, and a broad conclusion from that is that reionization should have been halfway over at something like a redshift of 8. And the final one is the ionizing emissivity. And so you can actually go out and measure the number of ionizing photons out there in the IGM at whatever redshift of interest you want. And these are some of the best measurements available from Becker and Bolton 2013, showing the emissivity as a function of redshift from 2 to 5. Measurements at higher redshifts aren't really there yet. There is one by Bolton et al. 2007 at redshift 6 that's an upper limit, but they assume a uniform ionizing background, which we don't think is true. So we did not make use of that. We just use these measurements at redshifts 2 to 5. And one thing I want you to notice is that these are pretty flat. That'll become important in a little bit. Okay, so how do we actually do this? We use this flowchart. I'm not going to talk you through it because that would take a long time. But the paper is out there. You can talk about it if you want to. But the key assumption, again, is that the escape fraction is dependent on the halo mass. And I just want to show you what that actually does. And so because it's the lowest mass halos that are the ones that have the highest escape fractions, the lowest mass galaxies actually dominate reionization. And so you've probably heard before, faint galaxies dominate reionization. But you're not talking about the same kind of faint that I'm talking about. So I'm trying to illustrate that in this plot here, which is showing the cumulative ionizing emissivity as a function of absolute magnitude. And the gray lines here are sort of representing previous work, which encompasses a lot of work, including that from myself. And the particular lines I'm showing are from Brant Robertson's paper in 2015. And the shading represents redshift. So this is 4, redshift 6, redshift 8, redshift 10. And so let's take a look at redshift 6. At redshift 6, 50% of your ionizing photons come from galaxies brighter than -18. Those are the galaxies we can actually see. 50% come from galaxies fainter than minus 18 too, sure, but the majority of the emissivity is coming from this range, let's say minus 16 to minus 20. But if you put the emphasis on the faint end and say photons can only escape from those on the faint end, then you get the blue lines that come from my model, and then you're really looking at the sort of ultra-faint regime between minus 12 and minus 15 or so. And so in this model, if it was right, it would mean that very, very faint galaxies are the dominant contributor. And so as I mentioned, this is a paper on the archive. Actually, just got accepted on Monday. So as soon as I can fix one plot, I will replace it up there with the accepted version. And so the upshot is it works in that we can match the constraints on reionization. And so I'll walk you through that pretty quickly. So the top plot is the reionization history or the ionized volume filling fraction. Here is the posterior for our model in blue, the upper and lower bounds of the shaded region, and I'm going to show this type of plot a lot, so I'll explain it for a second. The upper and lower bounds are the 68% confidence range, and then the shading denotes the shape of the PDF inside there. Okay, so it's not the full posterior, but it's the central 68%. So this is showing our reionization history. We match these upper limits here from Agree et al., and we finish by a redshift of 5.6. And we start at some early time. Of course, that's not constrained that well, but the key difference here is that it proceeds sort of much more linearly than a model where you need the more massive galaxies. And so in the previous model, you needed more massive galaxies to actually have time to form, to make their ionizing photons. And so reionization starts slowly and ramps up at the end. Where faint galaxies dominate reionization, you have faint galaxies early on. And so it simply proceeds a little bit faster, but still finishes on time. You might say, don't you make too many ionizing photons? And the answer is no. So this is our constraints on tau. And green in all of these are what we're using as constraints. I'm showing a bunch of tau values here. We're using the 2016 value from Planck. We are higher, but the discrepancy is only about 1.5 sigma. And when we look at the ionizing emissivity over here, purple is what comes from galaxies, red is what comes from quasars, and I'll show you what that looks like in a minute, and blue is the sum of them. And you can see we just sort of squeak in there, being at the 1 sigma bottom end of those constraints. You may wonder why our galaxy is going down when the galaxy luminosity function is going up, and that's because the faint end slope of the luminosity function is flattening as you get to lower redshift. And that's actually good because it means we don't exceed these points. So if you assumed something like the classical old model where everything is the same escape fraction, you'd get something like this gray line here, and it keeps rising and rising and rising to where it's at the upper 1 sigma end here. But remember, these emissivity measurements are flat down to redshift 2. And I didn't run my model below that, but they're going to keep going up. And you're going to make too many ionizing photons. And that's been a problem that I know has been bugging George Becker. I don't know how many people he complained about, but he complained to me about it. And I took him seriously. And Elizabeth Stanway's written a paper about this too, that you actually were making too many ionizing photons. And so this does actually solve that problem. So let's talk about some of the results from this. So this is the average escape fraction. So if we take all of the ionizing photons escaping galaxies in our simulation, or in our model, and divide it by all of the ionizing photons that are made. Blue is for all galaxies, purple are for sort of those ultra-faint galaxies, and red are for the bright galaxies. And so at redshift 4, you have an average of 1% of an escape fraction, so that's kind of consistent with the typical non-detection. And throughout the epoch of reionization, it's actually less than 5% on average, and then it gets as high as about 10%. At higher redshift, maybe 12 to 15% if you're looking at faint galaxies. Even though we don't input a redshift dependence, so the escape fraction is only dependent on halo mass, one falls out of this because the halo mass function evolves. So that's actually why you see this redshift dependence here. So escape fractions are lower than before. That was sort of the starting point here. There's no surprise there. What about the limiting magnitude? And so this plot illustrates those two different halo mass thresholds I talked about. Okay, so as you evolve from redshift 20 and on, this line shows the atomic cooling limit. Stars are never forming down here. Once reionization turns on, then you're going to suppress star formation at some photosuppression limit, and this blue shading is showing a one-dimensional posterior. So it really wants to be low. That makes sense because that gets you more ionizing photons. And so 8.5 was actually our prior. We didn't let it get below that. So it wants to be low. The one-sided upper limit is something like less than 9.4 in log. And this is what it means for the limiting magnitude. And so as a function of redshift, you can see the limiting magnitude evolves for a couple reasons. But the biggest one is it's moving from basically being at the atomic cooling limit to this photosuppression limit. But the key point is it's almost always at a fainter magnitude than minus 13. And so you're always forming stars and more galaxies. So you're forming stars and more galaxies. Those are the galaxies that have high escape fractions. That's actually how you do this. Or it's one of the biggest contributing factors. So that is limiting magnitude and escape fraction. There was one we were missing, which is C-ion. So we allow C-ion to evolve, and evolve it does. So this is our commonly assumed value here of 25.2. Red shows the evolution for bright galaxies and purple for faint galaxies. So it essentially prefers high values. That's not surprising. We need ionizing photons to make this work. Why could this happen? Lower stellar metallicities is an easy one. You can boost the ion if you assume that galaxies have contributions from binary stars, from the BPAS models. Faster stellar rotation can actually also contribute here too. So you might say those values are crazy, but when you look at the measurements, which are few and far between at high redshift, they're actually not crazy. The red squares show observed measurements of C-ion for bright galaxies, and it lies pretty well, maybe at the low end, but still consistent with our bright constraints. And there are two for sort of fainter bluer galaxies here in blue, which are, one of them is sort of as high here. And if you look at local galaxies that are extremely bursty, this was a paper by Izatov, they found that they had very high values, close to 26. And 26 was our cap. We didn't let it go higher than that. So this is, there's a lot of speculation in various parts of this talk. I would say letting this get this high is pretty speculative, but it's very, very loosely consistent with constraints we have. And as we'll talk about at the end, this is one, there are many excellent things that we're all going to do at JWST. Actually pinning down this quantity at reasonably high redshifts is one of them. All right, so let's talk about the AGNs. So here's that same plot I showed you before, even emissivity. And remember, we could lie between these two curves, and that's what happens. So the blue shaded distribution is our posterior, and it prefers something in the middle. So what does that actually mean? That means if we take the ratio of the emissivity from galaxies divided by that from AGN, galaxies still dominate. Galaxies, in fact, dominate all the way down to redshift 4.5 or so. It's only at redshifts less than 4.5 where AGNs really start to dominate the ionizing emissivity. And that's good for a couple of reasons. Number one, you don't have to go around and say AGN reionized the universe because they didn't. And number two, you actually don't ionize helium-2 too early. So actually, I'll just show you really quickly. The red here is the helium-2 reionization history. It finishes at about 2.7 or so, which is pretty consistent with observations. All right. So that's AGN. You might say, okay, you allowed those AGN. What happens if you turn them off? Well, I'm not going to turn them off, but I did do a model run where I forced it to follow this green curve here, and you actually do run into a problem, which is that some portion of the posterior does not finish reionization until redshift 4. That's what's being shown here. So the majority of it still works, but some of it doesn't. Okay. One thing I just want to point out briefly is there's not a lot of measurements here, and so it'd be great to improve that. And what you need to improve that are constraints on the faint end slope of the AGN luminosity function. And I had a student, Matt Stevens, who was working on that. That orange bar are his constraints. I don't know if we're adding or subtracting by putting a giant bar on there. But the problem really is distinguishing AGN-dominated systems from galaxy-dominated systems at magnitudes of -23 to -24, which are where these two luminosity functions intersect. So he actually fit the luminosity function simultaneously, and there's a degeneracy there that we're trying to resolve with spectroscopy. All right, so let's talk about now what we are doing to test this model. So it's a model. Models are fine, but we would like to make some predictions, which we have, and test to see if it works. So one big one is this model predicts that reionization is pretty linear or pretty smooth, and not that it ramps up at the end. So it predicts a fairly high ionized fraction of 80% or neutral fraction of 20% at redshift 7 or so. And so how can we actually measure that? One of the best ways to do it in 20 years will be from 21 centimeter line tomography. One of the best ways we can do it now is with Lyman-alpha emission. So it's been known for a while that Lyman-alpha should be a sensitive tracer of reionization because these photons are resonantly scattered. If you're looking at a source of Lyman-alpha photons and there's a neutral gas cloud in between you and that source, it's going to scatter those photons to very low surface brightnesses, and you're not going to see them, and some of them will be destroyed. So that's great. Also, it turns out that Lyman-alpha we think is relatively abundant at redshift 6. This is an oldie but goodie from Dan Stark showing the fraction of galaxies with detected Lyman-alpha as a function of redshift. Just take a look at the red ones. That's for reasonably strong lines of 25 angstroms, and it goes up from redshift 4 to redshift 5 to redshift 6. This was a guess for redshift 7. That's not what we see, which is interesting. Maybe it's reionization. We'll talk about that. But so it goes up from 4 to 5 to 6. And we think that's probably due to decreasing dust content in galaxies. It's certainly due to something in the ISM and not the IGN at those epochs. And so this is another oldie but goodie, but a simulation from Matt McQuinn showing you essentially what you see versus what's actually there. So this is showing you an intrinsic distribution of sources and all these panels as these little dots at 3 different regimes where the neutral fraction is 30%, 50%, or 70%, and then the bottom shows you what you observe. So when the neutral fraction is low, you see Lyman-alpha from everything. When it's very high, you see Lyman-alpha from almost nothing, and it's very, very, very clustered. So you're seeing it from only the ionized regions. So great. Okay. So of course, this isn't a secret. We've known of redshift 7 galaxies for over 10 years now. And so there has been a lot of work, a lot of telescope time, I think well-used telescope time, trying to measure Lyman-alpha at high redshifts. And I'm just showing you some of the successes here, multiple lines measured at redshift greater than 7. Okay. And so you might say that means that the IGM is pretty ionized, but a lot more than 4 sources had spectra taken of them. And so the conclusion is actually the opposite. The majority of galaxies are going undetected during this spectroscopic follow-up, leading to the inference that the IGM at redshift greater than 7 is highly neutral. This is just a figure from Charlotte Mason's recent work. There are a number of groups in the world doing this. I think hers is some of the best, using realistic models of reionization to try and constrain this. And you can see that this says the neutral fraction must be something like 50% at redshift 7. All right, so, but I think this is far from certain. So we're taking observed spectra of sources, and we're trying to turn them into constraints on the neutral fraction in the IGM. And so there are a number of systematic uncertainties and model dependencies here. And one thing that bugs me is that most of these constraints are based on non-detections. Of course, if we're doing everything right, those non-detections are highly constraining, but we need to be doing everything right. So some of the things that could go wrong. Number one, we don't have complete spectral coverage of the full redshift probability distribution function for these galaxies. They're pretty broad. A given galaxy that we say is redshift 7 might be anywhere from 6.3 to 7.6. And when we observe with most spectrographs, we have to choose a specific filter, a Y-band filter or a Z-band filter in the optical, or a J-band filter, and you often don't cover all of it. Second, or along with that, most of the time we're doing this from the ground. You can try and do it from space. We've detected a Lyman-alpha emission line at redshift 7.45 from space. It was really hard, and that line was really bright. So we do it from the ground because we can go deeper, but you have the night sky emission lines. They're very bright. At Mossfire resolution, R3000, they take up about half of your wavelength real estate. And then you couple that with the absorption bands between the different filters you're looking through. Number two, spectroscopic depths, for a high redshift person at least, they're often pretty shallow, something like maybe just a few hours. And there is an uncertainty in the depth of non-detections because it's dependent on the Lyman-alpha line width. One of the things we only recently figured out, which should have been obvious, is we were comparing our Lyman-alpha depth measurements to the MOSDEF survey, and they were going deeper than us in the same exposure time. They realized, all right, all their lines are unresolved. Lyman-alpha has a broad red wing, and so that hurts your sensitivity as well. Unknown distribution of Lyman-alpha kinematic offsets. So Lyman-alpha typically is gained a little bit of redshift by the time it escapes from the galaxy. And so that's another effect you have to try and model when you're going from observations to neutral fraction constraints. And sample contamination. What if all the things you don't detect Lyman-alpha from were really redshift 2 and not redshift 7? I don't actually think that's it, but I think it's possible for some sources, certainly not all sources. So we've been trying to improve on as many of these as we can, and the biggest thing we're trying to do is to get detections. And so over the past 5 or 6 years, we've been amassing as much Keck time as we can through some collaborators in UC, but also through NASA's Keck allocation. And we have tried to go very deep as we can in both the optical and the infrared. Alongside of that, we've also spent a lot of effort on improving the photoz's, specifically including the Spitzer IRAC photometry, and I'll talk about that in a second. But just to show you what we've got from something like 20 nights with Mossfire, I'm just going to talk quickly about 2 papers that In-tae Jung, who's my PhD student, who is defending in 22 days, so he's appropriately very stressed out right now. This paper's published, so he's not stressed out about this one. We looked at 4 sources that we had observed for over 15 hours with Mossfire, and we detected Lyman-alpha from 2 of the 3 that were bright and not from the one that was faint. So we're starting to detect more, and we can do very cool resolved Lyman-alpha studies. So this one on the bottom is one I had actually published before, and it did not look asymmetric at 5-hour depth. And now at, I believe, 16-hour depth, it's measurably asymmetric. And more exciting, this is his paper he's stressing about because he has to finish it in the next 3 weeks, is that when we look at all the sources with more than 10 hours of integration, out of 18 sources, we have Lyman-alpha detections in something like 10 of them. Okay, and so what we're finding is that when we go deeper, we're actually starting to detect Lyman-alpha. It's faint, and so the answer is certainly not that there's no attenuation by the IGM, but I don't think the answer is that there is 50%, a neutral fraction of 50%. That doesn't mean that the global neutral fraction is not 50%. All of these come from the same region of the sky, in Goods North. We had great weather in Goods North, lousy weather in Goods South, so it just so happens that we only have one line of sight. It's possible that that line of sight just reionized early. And so we need to repeat these type of experiments in more fields if we can. With Keck, here are just some examples of 1D spectra, but I'll move on. All right, so that's at redshift 7. What about at redshift 9? So the older model would say that reionization is not very well underway at redshift 9. My model would predict that maybe it's halfway done by redshift 9. And so is there any evidence that it's underway? Well, if reionization was half complete, you should have an awful lot of galaxies there doing that reionization, making those ionizing photons. The problem is, when people have done work at redshift 10, there's been a lot of discrepancy. And so some studies have found that the star formation rate density, which was kind of smoothly evolving from redshift 4 to 8, is falling off a cliff. And some studies, I'm only showing one there, the yellow point, has found that maybe it's not. Okay, so if this really was true, if it was falling off a cliff, that would be evidence, I think, in favor of late reionization, because you simply don't have many early galaxies, whereas if it was smooth, maybe not. Maybe there's plenty of ionizing photons. So what are we doing? We are actually trying to now enter ourselves into the redshift 9 to 10 universe in the candles fields. This is work that other people have done over the past couple years, but the new thing that we're doing is we're including the Spitzer IRAC photometry because it really helps with the photometric redshifts, and it really, really helps kick out contaminants. So I'll tell you why. So the reason why is if you look at a redshift 10 galaxy here in red and you compare it to the candles filter set, how many filters do you actually detect that galaxy in? 1, sometimes 2 if it's at redshift 9.5. You can just get it in the J band, but typically 1, okay? And so something that you see in only the H band, absolutely it could be a redshift 10 galaxy, could also be a really red redshift 2 galaxy. And so the way, it could also be a brown dwarf, which I also heard about this afternoon. So the way to get around that is actually to include Spitzer IRAC. Okay, Spitzer is fantastic. I can't believe we're talking about redshift 10 galaxies with a 0.8 meter telescope, but it works for bright things, and that's all I'm going to talk about today. And so this is showing you why. So the blue region here, that's a typical SED of like a redshift 8 to 10 galaxy, and you can, and then the, let's see, the light blue, green, and yellow are ML and T dwarf spectra, and the red and purple are either dusty or passive galaxies at low redshifts. And you can see in the single filter, you detect them with Hubble, and maybe the lack of a detection in the J band, they kind of all look the same. But as you go out to IRAC, they look very different. The low redshift red things are unsurprisingly very bright because they're very red, and the brown dwarfs typically turn over and start to fall off. And so you can actually distinguish between these with Spitzer IRAC photometry. And so here are some examples of how it works. I'm going to show you 3 galaxies that all look the same in Hubble. So they all will have a non-detection in the I band and also in V and in J. I'm just not showing it. And they'll also be detected in the H band. And so if you run a photometric redshift fitting code on just the Hubble photometry, you'll get this blue curve here that says, well, I think it's high redshift, but I don't know how high. And then if we put in the IRAC constraint, you'll see that it peaks up pretty nicely at redshift 8.5. And one reason why this gets very tight is you can see that the 4.5 micron band is brighter than 3.6. That's because there's very strong oxygen 3 5007 angstrom line emission in that IRAC band. So the nebular lines are bright enough, strong enough at high redshift to actually help with photoses, which is pretty cool. Here's another example where when we go to IRAC, it looks conspicuously big and bright, and unsurprisingly now the photosy prefers a low redshift solution. And you'll notice that it wasn't impossible before. There was a little peak there, but now we have more information, and it turns out that peak is strongly preferred. And here's an example where we didn't really know what it was, and then we observe it with Spitzer, or really we look at the S candles, very deep Spitzer data that's there in the candles fields, and we see nothing, and now it says, okay, it's got to be high redshift, because if it was low, you should have seen something. And so I've done this work, remade new catalogs, done IRAC deblending and everything, all of these new fields, and this is the sample that we have. I'm limiting this to magnitudes brighter than 26.5, which is where we're reasonably complete in all 5 candles fields, and we see a lot of bright galaxies. There are 13 of them, and if I compare them to the work previously done by Richard Bowens, he found, I believe, 4 or 5 in the same magnitude range. We're looking at the same galaxies, the same fields, different selection techniques, making use of the IRAC imaging. Okay, so you'll look at this, and you'll be like, well, Steve's full of crap, these must be low redshift galaxies. And I don't actually think that's the case. But I'll tell you why in a second. So let's do something a little silly and show you a luminosity function I made at a restaurant down the street from my hotel last night. This is not that. This is the published data. So here in brown is the redshift 10 luminosity function from Pascal Lucha's work, and these are his data points. In yellow is the redshift 9 luminosity function from Richard Bowens' work. This is what you would get from those smoothly evolving luminosity functions I showed you before, so 4 to 6 to 8 to 10. So you can see why they claim they see evidence of accelerated decline, because this is where 10 should be and this is where it is. And this is actually where we sit, at redshift 9 or so, okay? And so we're finding more. This is the part where you think I'm full of crap. I'm sorry, I totally blew that. Because you look at this and you're like, there's so many of these galaxies. How can they all be real? And so ideally, this is the point in the talk where I would say we have spectroscopic redshifts for all of them, and I'm glad to show them to you. That's not what I can tell you, but I will show you all the information we have on them and try and convince you that they're real. Are they all real? I don't know. There's 13 of them, maybe a few are contaminants, but no information we have now points towards that. Everything points towards them being true high-redshift galaxies. So before I do that, what does it actually mean if they're true high-redshift galaxies? So I think it can mean a number of things, but it could tell us that the star formation efficiency at high redshift is different than today. So this is the plot of star formation rate density, surface density versus gas surface density. This is the Kennicutt-Schmidt plot, and the Kennicutt-Schmidt law is this green line here. And what Rachel Somerville and her group has been finding is that to match the luminosity functions of galaxies at high redshift, you need this law to steepen towards higher values at higher gas densities. So as gas densities are higher, galaxies are better at forming stars. As you go to higher redshifts, gas densities are higher. So therefore, higher redshift galaxies are better at forming stars. And this is just, this is work by her student, Aaron Young, at Rutgers in the CCA, showing that their model, where you get that upturn, matches the observations at a whole bunch of redshifts they have. And so I asked Aaron, I said, how many galaxies would you predict in candles at these magnitudes I'm talking about? And he said he would predict 8 at redshift 9 or higher at the magnitude I'm looking at, and I find 13. And so that's more or less consistent with this model. If I really want to be provocative, I would say maybe it needs to steepen even more. And we have one galaxy at brighter than 25, and he predicts essentially 0. And so certainly there's some cosmic variance in here, but I think that this implies that this steepening may actually be needed to match these observations. Okay, so does this hold up? All right, so let's take a look. I'm actually going to show you some galaxies. I'm going to show you a lot of plots like this, where the bottom here or the left side shows you the Hubble imaging. So that's V band, I band, Y band if it's there, J, this F140 JH band, and H. And ideally, we should see nothing, basically nothing in the top row and something in the bottom row. This F140W band I didn't show you before. It's only 800 seconds, yet we still see it because these galaxies are bright. And I'm showing you the SED on the top. Okay, so here's the near-infrared detection. Here are the upper limits. And then we have IRAC over here. This source is horribly blended. This is our best attempt at deblending. So this is using T-phot. And this particular image down here is showing you the source of interest is left in and everything else is subtracted out. And so you can see when things are really big and bright and close by, you actually don't do a great job with your deblending. Finally, I'm showing you the photoses here. Blue, which is hard to see, is without IRAC, and red is with IRAC. And so this one has a Lyman break of over an order of magnitude in flux, right? And that's hard to do with anything except a high redshift galaxy. This one also has a spectroscopic confirmation at redshift 8.68. So this was a galaxy that Adi Zitrin confirmed in 2015 from Lyman-alpha. So even though the IRAC is maybe a little bit shady there, the deblending, it's actually confirmed already. This is my favorite one. It's extremely bright. It's 25.4 in the H band. You see it in the J band, but it's fainter. Okay, and then you don't see it here. So same thing, extremely strong Lyman break. This one is not crowded in IRAC, and look how much brighter the 4.5 micron flux is than the 3.6. And so that's got to be O3 at redshift 8.5 to 9. Here's another one, same thing, and another one, and another one, and another one. Interesting, out of the 13 sources, 7 of them are in one field, the extended Groth strip field. Cosmic variance, these things are massive, they cluster a lot. I don't think that's actually unsurprising. But you may call that a cause for concern. Specifically, all of them are in the candles wide fields. None of them are in the goods fields, where the data is actually better. And so that's something to keep in the back of your mind. This is the brightest source in our sample. It's actually in Cosmos. Here it is in Hubble in all of its images. Here it is in IRAC. It's fairly well deblended. Looks the same here. Here's its P of Z. This one is super intriguing. It's at the highest redshift we have, redshift 9.4. We actually, those 2 orbits of Hubble data I mentioned at the beginning, they're coming in next week, and they will slide in right here in the F098 medium band, and we're hoping to not detect it. We didn't put that in the first line of our proposal, but we're hoping to not detect it, and we'll put an upper limit right here, and it will make it essentially impossible that this is low redshift. We also put in, for cycle 27, for GRISM observation for this, and for Keck as well, Keck-NIRES, to try and measure a number of lines, because it looks like an AGN. It's very compact. Its SED is very red. It's what I think of when I think of lower redshift AGN, only now we're talking about at redshift 9. And so with Keck, we're hoping to see evidence for carbon-4, helium-2, nitrogen-5. maybe some other lines. All right, there's our wideband data there. Hopefully an upper limit, not a detection. Okay. So I would like to take spectra of these, all of them, to show you. We could do ALMA, and for the ones in UDS and Cosmos, we had proposed for ALMA just a couple weeks ago. EGS, we can't do ALMA. We will propose for NOEMA once band 4 is available and can do oxygen 3, but for now we're stuck with Lyman-alpha. And so my student Rebecca Larson has been leading a Lyman-alpha follow-up program of these sources, and the idea is at redshift 9, we ought to be able to tell the difference between 20% ionized, where you may be looking at a region like this with very few ionized bubbles, or 60% ionized like this. And so there's Rebecca. She's been leading a series of Keck programs. She's gotten 6 nights through NASA and just put in for 2 more. Maybe is the answer here. So this is probably one of our best. I won't even call it a detection because it's only about 3 sigma, but we see a little blob there. This was that brightest one in the EGS that I showed you. So stay tuned for that. The Keck reduction pipeline for MOSFire is actually pretty good, but we're trying to find every way we can to squeeze every little bit of signal to noise out of these data. All right, this is really hard. It would be better with GMT. That's basically what this is showing you for 2 reasons. Number 1, 25 meters is better than 10, of course, but number 2, with the manifest fiber system, I'm preaching to the choir here, GMT is awesome, right? When TMT is built and ELT is built, we're not going to have it in collecting area, but we will have it in survey area. Manifest can patrol a 20 arc-minute field of view, and I've just stuck that on this reionization image. So if you looked with Keck, maybe you would have seen something ionized and thought, oh, everything's ionized, or maybe you looked here and you thought, oh, everything's neutral. With GMT, even in just one observation, you'll be able to get it all, and you'll be going much deeper. So that's in the middle of the next decade. So let's talk about something that hopefully is not in the middle of the next decade, which is the James Webb Space Telescope. And so looking at all of this high redshift stuff that I've talked about, how could we be a little bit less speculative and have better observations? So one of them is, for these galaxies at redshift 9 to 10, we need deeper imaging, of course, but we also need to cover these redder wavelengths, these Spitzer wavelengths at Hubble-like PSF, which we'll get with NIRCam. We need deeper spectroscopy. We'll go deeper with GMT, but even with NIRSpec, even though it's a small field of view, we can still go deeper on Lyman-alpha at redshift 7 to 10. But I think even more exciting is we can get full restream UV spectroscopy for hundreds, maybe even thousands of galaxies throughout this era from redshift 4 to 10 to understand how the ionizing conditions evolve in these galaxies, not only to measure C-ion, but also to look for evidence of faint AGNs. And so these science goals were some of the motivation behind our ERS program that Sandro mentioned. So the name of our ERS program is Sears, or the Cosmic Evolution Early Release Science Survey. And this is a 63.2-hour program that if the telescope launches in March of 2021, and if there are no problems, I'm sure nothing bad will happen, we will observe in December of 2021. And we will observe the EGS field, all chosen before we actually knew there was perhaps an overdensity of redshift 9 galaxies there. So that was kind of fortunate. So this is the layout of what Sears is going to do, and we pitched ourselves around being the survey ERS program. We want to demonstrate efficient extragalactic surveys with JWST. And so the grayscale in the background shows you the H-band exposure map of the EGS field, and this shows how we will observe in December of 2021. So we're going to do 6 pointings of NIRCam here, labeled 5 through 10, and in parallel, we'll be doing NIRSpec, shown by the red squares. Actually, formally, NIRSpec is prime and NIRCam is parallel, because that's how they like it. In imaging, we'll do 5 to 6 filters from 1.2 to 4.5 microns. So F115W is the bluest broadband, and we'll go all the way out to 444, and we will do F410M in some of the fields. With NIRSpec, we'll do R of 1,000 spectroscopy in all 6 pointings with all 3 R of 1,000 gratings, and we'll also do R of 100 prism in 4 pointings. So that's 6 NIRCam pointings. And the other 4, numbers 1 through 4 up here, we're going to do MIRI in parallel shown here. 2 of the MIRI pointings, number 1 and 2, we're only going to use the 2 bluest filters, 560 and 770, and go deep. That's for sort of the high redshift science, measuring old stars, better constraining the mass of old stars. And the other 2 pointings, we're going to do almost all of the filters from 770 out to 2100 for redshift 1 to 2 dust emission science. And finally, we're going to do some GRISM with NIRCam. So NIRCam, you can do GRISM spectroscopy, slitless GRISM spectroscopy with the long wavelength channel, and we're going to do that in these middle 4 pointings here with 1 filter, F356W, which will do a lot of cool stuff. What I'm most excited about is look for serendipitous oxygen 3 emission lines from redshift 5 to 7. And more exciting, we'll even be able to do that with F44W out to redshift 9, but the background is higher. And at the exposure times we're working with here, we think we're going to get more science out of that. But everybody else should be proposing for very deep F444W GRISM spectroscopy. If you want to know more, talk to me, or you can go download our APT file, which is available. So just a small sampling of the primary science goals. So of course, what I'm most excited about is better constraining the redshift greater than 10 universe. And we looked at every model under the sun that we could find to predict how many high redshift galaxies we should find. And looking at the range of these models, we should find anywhere between 5 to 50 galaxies at redshift greater than 10 within Sears, and that's great. I sort of hope for 50 because you can do a lot more than them. But either way, we're going to constrain these galaxy formation models that are showing here. And if we detect some, hopefully, we'll have great targets for cycle 2. With near-spec and near-cam GRISM, we can not only do Lyman-alpha, but we can detect a lot of emission lines. So this is showing you a GRISM simulation, O3 there plus H-beta, even O3 for 5007 from a fainter source. And then this is showing you two different models at redshift 6 where we change the ionization parameter by 1 dex, and it shows you that the ratio of oxygen 2 to neon 3 changes by a lot when you change the ionization parameter, so you can use that to measure them. I just like to look at this and count up the emission lines. I mean, we're looking at redshifts where maybe we can see Lyman-alpha just barely, and now you can see 10 emission lines. And so there's a lot of cool stuff you can do, even if you just want to count emission lines. And finally, if we talk about galaxy morphologies in the mid-infrared, this is a real observation of a redshift 2 galaxy at Spitzer, 3.6 microns. It's beautiful. This is what you'll get with near-cam at the same wavelengths, exquisite resolution. And the same thing holds true if you move out to 20 microns. Here is Spitzer MIPS, real image, and this is a model of some real galaxies in the Candles fields of how they'll look in MIRI, in the slightly redder mid-infrared. So with that, I'll just end with some take-home points. So if we assume that the very faintest galaxies dominate emissivity, reionization starts earlier, proceeds more linearly, and completes on time by redshift 5.6. So this predicts that AGNs are necessary to assist with the end of reionization, and we do see some evidence of that. That the IGM should be 70 to 80% ionized at redshift 7. I'm not ready to say we see evidence of that, but we are uncovering more Lyman-alpha emission lines. And that significant star formation is happening at redshift greater than 9, and I think we do see evidence with that. If you don't like any of this, wait 3 years. We'll have a much better answer for you with JWST. Thank you. Erica?
So you showed the template SEDs for the redshift 2 galaxies and then the high redshift galaxies. Mm-hmm. And maybe it's just how you scaled the scale on the y-axis, but all the redshift 9 galaxies looked more similar to the redshift 2 galaxies, like they were red and IRAC.
This one?
Yeah. And so in the do you have actual SEDs of the galaxies with the points and the templates plotted on there?
Oh, not in the talk I don't, but I can find them and show them to you. I don't think I do. Talking about like
because you had the SEDs, but then there
these
were
ones.
fits on them. Yeah.
Yeah, right. No. So I can show them to you. And so you can see in some of them, let's see if we can find a good one. I mean, there's the low redshift solution. I can see it. Maybe you can't. There is a low redshift solution there.
Yeah, I was just wondering what it looks like on the actual.
Yeah, it's pretty red. It comes up like that, and then it starts to turn over here. And so usually it's the IRAC which is disfavoring it. But yeah, I'd be happy to show this to you.
I'm wondering about the quasar contribution to reionization. Have you tried, what assumptions did you make regarding low mass n, like intermediate mass black holes? Because this might be important, like if the mass function steepens and they accrete and they produce a lot of hard photons.
Yeah, so 0. So we're basically, the only thing we use in this model was the integrated emissivity. And so you can get that wherever you want. I feel like we have a pretty good idea of the abundance of massive quasars, and so I think it has to be the lower mass quasars. At some point I tried to look into how well we could constrain the faint and slope of the AGN luminosity function needed, but that was not very productive, to put it that way. So I don't know what constraints we can place on that. In principle, you ought to be able to place some. I think they're just going to be pretty broad.
Yes? What do you make of the damping weighing constraints from quasars on the neutral fraction?
Yeah.
The redshift 7.5 quasars, they seem to suggest very high neutral fractions.
Yeah, so I have a plot that I thought I put in here, but maybe not. I have a plot, I'll show it to you later. where I compare our observations to those quasar observations. So certainly the damping wings imply higher values of the neutral fraction, something like 50%, consistent with Charlotte's Lyman-alpha measurements. Their uncertainties are large, actually much larger than the Lyman-alpha based measurements. There are other things I could rattle off, like you have to intrinsically model the quasar. There's a line of sight dependence that they try to correct for. I think if you get samples of 10 to 20 and they all imply that, then that starts to really make a dent. And then that's the point where you actually start using those to really constrain these analyses. You just have to find 10 to 20 redshift 7 to 8 quasars.
Any final questions? Okay, then let's thank Steve again.
Thank you.